increasing and decreasing. The sign of the derivative at a point on a curve can tell us whether a curve is increasing or decreasing at that point. So here we have a curve, and here we can see the tangent drawn in, the tangent which is the derivative, and we can see that it's going upwards. So we have an increasing curve. Likewise, over here we have another curve with another tangent, and we can see that the tangent is going downhill. So the slope is going downhill, the slope of the tangent is going downwards, it's negative slope. So we have a decreasing curve. A curve is increasing, i.e. going up as we go from left to right, at a point if the tangent to the curve is also increasing. So the curve is increasing at a point, at a certain point, this point here, if the tangent is increasing. Another way of saying this is that the tangent has a positive slope. So the slope of the line is positive, it's going uphill. Thus, dy dx, the derivative, or the slope, is positive at that point. We can also say that the curve has a positive rate of change at the point. So it has a positive rate of change. Likewise, the curve is decreasing, i.e. going down as we go from left to right, if the slope of the tangent to the curve is negative. Thus, dy dx is negative at that point. We can also say that the curve has a negative rate of change at the point. So increasing and decreasing. Explain why the curve y equals 3x plus 1 over x minus 2 is decreasing for all x values elements of the real number set where x is not equal to 2. So we can't have x equal to 2 because we'd have 2 minus 2, which is 0, and we cannot divide by 0. Any mention of increasing or decreasing means we should examine the sign of dy dx. So have a look and see, is it a plus or a minus? So y equals 3x plus 1 over x minus 2. 3x plus 1 is the u, and x minus 2 is the v. So we're going to use the quotient rule. So v is x minus 2, we write that down with brackets. Du dx, we differentiate u with respect to x, so we get 3 with brackets. Bring over the minus, then write down the u, which is 3x plus 1 with brackets, and then dv dx, differentiate x minus 2, we just get 1. And that's all divided by v squared, so all divided by x minus 2 squared. So next we multiply out the brackets and we simplify. X by 3 is 3x, and 3x minus 3x, the x's will cancel. Minus 2 by 3 is minus 6, minus by 1 is minus 1, and minus 6 minus 1 is minus 7, and that's all over x minus 2 squared. As minus 7 is less than 0, so the numerator is less than 0, and x minus 2 squared is greater than 0, so the denominator is greater than 0, for all x values elements of the real number set where x is not equal to 2, dy dx is therefore less than 0, because a minus divided by a plus gives a minus. So the derivative is less than 0. The derivative is negative. And we know that a curve is decreasing where dy dx is less than 0, where the derivative is less than 0 is negative. So dy dx is less than 0 for all x values elements of the real number set where x is not equal to 2. Thus the curve is decreasing for all x values elements of the real number set where x is not equal to 2. So we have explained why this curve is decreasing. Differentiation can now be used to verify some results we obtained when investigating graphs in algebra and trigonometry. So this is where differentiation can pop up in other chapters. For example, by differentiation, we can verify that a quadratic curve is increasing on one side of its turning point and decreasing on the other side. Another case is highlighted in example 2. So f of x maps to e to the power of ax, where a is not equal to 0, is a constant. Verify that the curve y equals f of x is increasing for all x values elements of the real number set if a is greater than 0, and is decreasing for all x values elements of the real number set if a is less than 0. So the curve is y equals e to the power of ax. So we're going to differentiate using the chain rule. So we write down what we're given, which is e to the power of ax, and we multiply that by the derivative of the index. So the derivative of ax is a, and then we multiply them together, so we get a to the power of x. So as e to the power of ax is greater than 0 for all x values elements of the real number set, the sign of dy dx will depend only on the sign of a. So it depends on what this a is, the sign. If a is greater than 0, then dy dx is greater than 0, and so the curve is increasing for all x values elements of the real number set. And if a is less than 0, then dy dx is less than 0, and so the curve is decreasing for all x values elements of the real number set. So here we just have a few exponential functions just to remind you what they look like as curves. So this pink one here is y equals 2 to the power of x. This navy one here is y equals 3 to the power of x. This red one here is y equals a third to the power of x. And this green one here is y equals a half to the power of x. So notice that they all cross the y-axis at 1 and that they never touch the x-axis. That they continue to get closer and closer and closer and closer to the x-axis, but they should never actually touch it.